You are traveling at roughly 1,000 miles per hour. If the vehicle you are riding on slams on the brakes, you would die instantly. But look around. The room you are sitting in feels perfectly, comfortably motionless. Your coffee isn't spilling, the floor isn't vibrating. That stillness is a trick of physics. You are on the surface of a planet spinning at equatorial speeds of 1,000 miles an hour, dragging the entire atmosphere and every drop of ocean water right along with it. We are biologically incapable of feeling constant velocity. Our sensory systems simply ignore it, making our own bodies highly unreliable narrators of physical reality. Isaac Newton outlined exactly why we survived this ride. The first law of motion, inertia, dictates that an object moving at a constant speed stays in motion until an external force violently halts it. If the Earth's bedrock locked into place this second, every building, tree, and person not firmly bolted down would continue tearing eastward at supersonic speeds. The planet's spin naturally pulls ocean water toward the equator, creating a massive bulge. Without centrifugal force, that bulge flattens out, sending miles-high walls of displaced water rushing directly toward the North and South poles. The air above us holds that same momentum. The atmosphere would keep sweeping over the stationary ground, generating global windstorms faster than the most violent hurricanes ever recorded. All of that catastrophic potential energy is sitting right in front of you. It is simply hidden by the mechanics of continuous, unaccelerated movement. Think of flying in a commercial jet at 500 miles per hour. If the flight is perfectly smooth, pouring a cup of coffee looks exactly like it does in your kitchen. The liquid falls straight down. As long as the cabin walls aren't shaking, your eyes tell your brain you are stationary. You process movement strictly relative to the objects immediately around you, ignoring the sky outside. Psychologist Irvin Rock studied this exact phenomenon, induced self-motion. He found that our cognitive decisions about our own speed depend almost entirely on visual cues in our immediate environment. If the background doesn't shift, we assume we are at rest. The only time biology alerts us to movement is when our speed actually changes. Your inner ear, your vestibular system, detects acceleration and deceleration. It feels the plane taking off, but goes quiet once you hit cruising altitude. Because the Earth never hits the brakes, we are trapped in a biological illusion, meaning it takes a purely mechanical proof to bypass our flawed senses and expose the spin. On this overhead vector map, Earth spins beneath its atmosphere. The Coriolis effect causes hurricane winds to curve right in the northern hemisphere, but mapping weather takes vast distances. 19th century physicists wanted to prove this rotation locally, in a single room. In 1851, French physicist Léon Foucault designed a device to do exactly that. He secured a 67-meter wire to the dome of the Pantheon in Paris, attaching a heavy brass-coated lead bob. Once released, the pendulum swings in a straight line. The bob's inertia keeps its oscillating plane perfectly fixed in space, unbothered by the buildings surrounding it. As the hours pass, the point of the bob appears to slowly rotate across the numbered dial on the floor. But the pendulum hasn't changed direction at all. The floor of the Pantheon, and the Earth itself, is literally rotating beneath the freely swinging weight. Foucault's pendulum provided direct, mechanical evidence that our stationary feeling is a biological lie. The ground beneath our feet is a massive planetary carousel. This raises a strange, unsettling question. If the pendulum's swing remains completely fixed in space while the planet rotates around it, what exactly is it fixed to? Mach's principle proposes that inertia is a cosmic phenomenon, where the gravity of all distant matter in the universe provides the resistance that keeps a pendulum swinging in a steady line. That means the heavy brass bob swinging in Paris is orienting itself to the collective mass of the cosmos. Its steady path is anchored by the gravity of distant galaxies spread across the deepest reaches of space. To find the ultimate benchmark for this motion, we look past the stars to the cosmic microwave background. This remnant radiation from the Big Bang provides a universal reference for the entire cosmos, acting as a modern absolute reference frame that reveals how fast we are moving relative to the universe's earliest state. The feeling of sitting perfectly still in a quiet room is an illusion hiding a profound connection. Your local physics are anchored to an invisible web spun by the edge of the universe, and you are traveling through it at 1,000 miles an hour.